welcome. In this video, we're diving into one of the most important rules in calculus, the chain rule. In this video, I'll walk you through the basic rule, and then we'll hit 5 examples students typically struggle with, from powers of trig functions to exponential layers to product and chain rule mix-ups. With that said, let's dive right in with the definition of the chain rule. The chain rule is the derivative rule which allows us to take the derivative of compositions, where one function is sitting inside of another function. So here we have the derivative of f of g of x, where g is not being multiplied by f, but it's sitting inside of that function f. And when we have this situation, what we want to do is we want to start with the derivative of the outer function. So here the outer function is f, so we're going to start with the derivative of the outer function f prime. And then the important part of the chain rule is then we want to leave the inner function alone. So here that inner function is g of x, and we're going to leave it alone inside of this new derivative. All right, and now the last part is we're going to tack on our chain. So we are going to multiply by the derivative of the inner function. So here our inner function is g of x, so we're going to multiply on the outside here by g prime of x. And this is what we typically call tacking on our chain. We're multiplying by the derivative of our inner function. All right, so there's our chain rule. And as you can see, the notation of the chain rule can look a little scary at first. So what we really want to do here is anchor this with some examples. So let's dive into our first example. So here we have the derivative of x to the fourth plus 2x, all raised to the 8th power. So in this problem, we have an 8th power, like x to the 8th, but it's not just x to the 8th, it's a whole other function, x to the 4th plus 2x, which is being raised to the 8th. So that 8th power is our outer function, and we want to start with the derivative of an 8th power. Well, that's just the power rule. The 8 will come down as a multiplier, and then for the new power, we're going to subtract 1 from 8, so 8 minus 1 is 7. All right, so that's the derivative of an 8th power. Now the chain rule says that we're going to leave the inner function alone. So our inner function here is x to the 4th plus 2x. And now we need to remember to tack on our chain, which is the derivative of that inner function. So we're going to multiply by x to the 4th plus 2x prime. Now you may be able to do this derivative in your head, but I recommend using the prime notation, especially at the beginning in your notes, and as you get used to the chain rule, you can stop using the prime notation so much and just start doing these derivatives as you go. All right, so to finish off this problem, all we have to do is copy the stuff that we're not doing any more derivatives for. So namely the 8 x to the 4th plus 2x, all raised to the 7th. That's all done. And all we have to do is this little derivative of x to the 4th plus 2x, our chain. So the derivative x to the 4th by a power rule is 4x to the 3rd. And then the derivative 2x, the derivative of constant times x is just the constant, so plus 2. Okay? And there it is. There is our final answer using a chain rule. Okay? So let me throw up the words for the chain rule again, and you can kind of see where all these parts came from. Okay, so here are the 3 key parts of a chain rule problem. We located the outer function, which was an 8th power, and we took the derivative of that 8th power. Okay. When we did that, we left the inner function alone inside of that outer function, and then on the end, we tacked on the derivative of the inner function. All right, so that's the general steps of a chain rule. But let's move on to some more complicated problems that typically throw students off when using the chain rule. Here we have the derivative of secant of x cubed. Now when we say secant of, that implies that there's a function sitting inside of it, namely x cubed. Now one of the other things you can do to identify what is your inner function and what's your outer function is you can pretend that you're plugging in an x value. So say we're plugging in x is equal to 2. Well, the first thing that we would do is we would cube it. So that's our inner function. And then we would do the secant of that number. Okay, so that last thing that you do, that is your outer function. So in this case, secant is our outer function. Now trig functions are one of the first places where students start to struggle on the chain rule, and I think it's partially with how you learn your trig functions. So when you say the derivatives of your trig functions, try to leave off the x's. So don't say things like the derivative sine of x is equal to cosine of x. Say things like the derivative sine is cosine. Okay? And then you will naturally just fill in the inner function. So here I want to start off with my outer function, secant, and I want to start with the derivative of secant. Well, in general, the derivative of secant is secant tangent. Okay, so I just start off with secant tangent, and if you look at that, that doesn't make any sense. Secant, tangent both need something inside of it. And again, when we're using the chain rule, that inner function doesn't change. It just goes inside of each one of these functions. So we're going to get secant of x cubed, and then same tangent of x cubed. Okay, so that is taking the derivative of the outer function and leaving your inner function alone. And now we need to tack on our chain, the derivative of what was sitting inside of our trig function in the first place, so the derivative of x cubed. Okay, so use that prime notation to just kind of slow yourself down. And now all we have to do to finish this problem off is figure out the derivative of x cubed. And that is just 3x squared. Okay. Now, when you're writing out your derivatives of trig functions and algebraic functions, trig functions do tend to go in the back. So normally here I would move my 3x squared to the front of my function, because normally you put numbers in the front and then powers of x's, and then my trig functions in the back. So you would typically see your answer written as 3x squared secant of x cubed times tangent of x cubed. All right, so let's take a look at a problem that a lot of students struggle with the first time they see it, and that is the derivative of sine squared of x. And the tricky part about this problem is the fact that that sine squared, okay, is shorthand for really sine of x all squared, okay? And if we write it this way, it's much easier to identify what is our outer function and what's our inner function. Namely, if we're trying to compute with this and we plugged in, say, pi for x, we would first have to figure out what sine of pi was, and then we would square that whole result. So that last thing that we do, that square, that is our outer function, okay? So we're going to start with the derivative of the outer function, which is just a power rule. So the power rule says that that exponent 2 comes down as a multiple. Then we're going to subtract 1 from the power, so 2 minus 1 is 1, and that's going to become our new power. Okay? Now, the chain rule says we're going to leave that inner function alone. Sine of x just sits in there, and then we're going to tack on our chain. We're going to multiply by the derivative of sine of x. Now again, as you're beginning your notes, it's really helpful to use that prime notation so you can see where all the parts come from. So here we have 2 sine of x raised to the first, which is just sine of x, and then multiplied by the derivative of sine of x, that is cosine of x. All right, so again, the key here is to recognize that this square, sine squared, is really shorthand for all of sine of x being squared. Once we do that, it's very easy to see what is our outer function and what is our inner function. All right, let's take a look at a couple complex examples. We'll start here with the derivative of the natural log of x cubed tangent of x. Now, the first mistake that students typically make on this is a misunderstanding of what the derivative of the natural log says. So they remember the derivative of the natural log of x is equal to 1 over x. So that is just the derivative if you have the natural log of just x. But in general, what this natural log derivative does, it sends what's inside of your logarithm down to the bottom of a fraction. Okay, so that is generally what a logarithm derivative does. It sends the inside to the bottom. All right, so here with the natural log of x cubed tangent of x, the derivative of this is not 1 over x, it's what's inside the logarithm. X cubed tangent of x goes to the bottom of the fraction. All right, now we need to remember the chain, and the chain says to take the derivative of the inside, and that will go on the top because it's being multiplied. So we're going to take x cubed tangent of x and we're going to take its derivative. Okay. Now I want you to pause, forget about the denominator here, and just look at that derivative that we have left, x cubed tangent of x. Pause for a moment and see if you can figure out what rule we need to take that derivative. All right, so hopefully you notice that that is a product. It's x cubed times tangent of x. And one of the ways to help you identify those things is to take those little pauses. Take a breath, look at that prime as its own little problem, and think, what rules do I need to do this problem? So here on the top we have a product rule, and the product rule says it's the derivative of the first function times the second function left alone. So we're going to take the derivative x cubed, we're going to leave tangent alone, plus we're going to leave x cubed alone, and then we're going to take the derivative of tangent. Okay? And again, that is the derivative of the top, or the numerator, and the bottom, we've already finished that. We don't have to do any derivatives down here, so we just need to recopy that. Okay, so now we're going to take those two derivatives that are left on the top. The derivative x cubed is 3x squared, tangent of x, okay, and then plus x cubed left alone, and the derivative of tangent of x is secant squared, and then all of this is over x cubed tangent of x. Okay. Now, more than likely, if you look this answer up or you type this answer into, say, a homework program, this is not the simplified version of the answer. But for your notes, we're really just focusing here on doing these derivatives. So this is good enough for this purposes, getting used to actually doing the derivatives. All right, so another type of example that students typically struggle with the chain rule is derivatives of exponential functions. So here we have the derivative of e to the x squared sine of 5x. Now the derivative of e to the x is pretty simple. The derivative of e to the x is just e to the x. But the generalized chain rule form of that says that if you're taking the derivative of e to a power, okay, so not just x, I'm just going to write a u for a general power, the derivative of that is e to that same power, so it's basically leave that inner function alone, and then tack on the derivative of the power. Okay, so in words, when I say the derivative of e to a power, I say the derivative of e to the power is e to the power times the derivative of that power. All right, so let's use those words to take this derivative. So the derivative of e to a power is e to the same power, so e to the x squared sine of 5x times the derivative of that power. And again, here I'm going to leverage prime notation to slow my mind down, and that way hopefully I don't miss any rules that I need to apply. So again, we're going to pause here and just look at x squared sine of 5x prime and think about what rule you need to use. So hopefully taking that pause, looking at that derivative, we again notice that we have a product rule, x squared sine of 5x being multiplied by each other. All right, so taking that derivative, we're going to need a product rule, but first all we have to do is recopy this e to the x squared sine of 5x, okay, and then we're going to multiply by this product rule. Again, the product rule is the derivative first, so the derivative x squared. And again, I'm going to leverage prime notation here to kind of slow myself down. So derivative x squared times sine of 5x left alone, plus x squared left alone, times the derivative of sine of 5x. Okay. Now again, take a moment. Anytime we use this prime notation, just take a moment and look at those derivatives and think about the rules you need to use. Now, for the first one, that derivative is pretty straightforward. The derivative of x squared is just 2x. Again, I'm just doing some copying here. But the derivative of x squared is 2x. Sine of 5x is being left alone. Then x squared is being left alone. And then here, what is the derivative of sine of 5x? Well, it's not just sine of x, it's sine of something more complicated. So here I need another chain rule. So the derivative of sine is cosine. Again, I'm going to leave that 5x inside of it. And then I'm going to multiply by the derivative of 5x. Now the derivative of 5x is just 5. And since I'm at the very end of the problem, I'm not going to use another prime notation there. I'm just going to write out that derivative. It's pretty straightforward. Okay. Again, we might be able to do some factoring or remanipulation of this, but that's essentially what goes on with all these products and chains being linked together. For our last example, I want to take a look at inverse trig functions because inverse trig functions are another example of the chain rule where students really struggle with. So, for example, they know that the derivative of arctangent of x is equal to 1 over 1 plus x squared. Now, that is if you have x inside of there, then you'll get x squared over here. But really that x is a variable, so whatever you put inside that arctangent is going to get squared over on the other side when you take its derivative. Alright, so let's use this rule to take the following derivative. The derivative of e to the 5x times inverse tangent of x squared. So first what we'll notice, before we can even get to that inverse tangent, we have an e to the 5x. It's not inside of inverse tangent, it's being multiplied by it. And because it's being multiplied by it, we're going to have to use the product rule. So we have e to the 5x as our first function, and then inverse tangent of x squared as our second function. All right, again, I'm going to leverage prime notation here. I'm going to just write out the product rule. E to the 5x, the derivative of the first function, times the second function being left alone, so times inverse tangent of x squared, plus I'm going to leave my first function alone, e to the 5x, and then I'm going to multiply by the derivative of inverse tangent of x squared. Okay, so I'm just going to write this out in terms of prime notation. Again, we're going to take a mini little pause here, look at those two derivatives that we have left to do, and think about what rules we need to do them. All right, so for our first derivative, the derivative of e to the 5x, again, the derivative of e to a power is e to that same power times the derivative of the power. So the derivative of 5x is just 5. Okay. Now inverse tangent is being left alone, so inverse tangent of x squared just sits there. All right, so now we add on e to the 5x being left alone, and now we're going to take the derivative of inverse tangent. Now again, the derivative of inverse tangent is 1 over 1 plus, now it's not x squared, it's whatever's inside of inverse tangent that's being squared via the chain rule of that inner function just sitting there. So x squared squared. Okay. Now we're going to multiply by the derivative of that inner function, so the derivative of x squared. Okay. Now I am going to do a little bit of simplification here. It's mainly just copying and maybe moving like a 5 to the front because constants normally go in the front. So 5 e to the 5x inverse tangent of x squared plus e to the 5x times the derivative of x squared is 2x, and that can land on the top of this fraction. And then 1 plus x squared squared. When I raise a power to a power, I multiply those, so x to the 4th. Okay. Now we may be able to do a little more simplification, like factoring out that e to the 5x. But again, this video is not about simplification. It's about using the chain rule in more complicated scenarios. So I hope you found this video helpful. Now, if there are other examples of the chain rule or other rules in calculus that you need help with, please feel free to drop those in the comments. And finally, if you need more help with your chain rule, please check out my video on learning the general forms of your derivatives. And as always, if you like this, please like the video and subscribe to my channel for more content in the future.